Hi, I'm Rob Simmons, Product Manager with Garrett Advancing Motion. The topic I'm going to present is turbo system optimization. While turbocharger selection is a critical part of your project, selecting the correct mating components is equally as important. Optimizing the entire system ensures that the engine will make the target horsepower and everything functions properly. What I hope you take away from this is not only a better understanding of turbo system components, but also where you can find this information for future use in projects. The areas that I'm going to cover are based on questions that we've received during trade shows and races, as well as areas I feel are commonly overlooked. So let's get started. This is an outline of what will be covered: the Garrett Motion website, application information, turbo match. Then I'll cover specifics about individual components such as the air filter, water lines, and wastegate, common causes of oil leakage. This is important because other components or subsystems can cause oil leakage at the turbo. I'll go over system testing and monitoring and the 11-point checklist. This is a checklist for items to keep in mind when designing your system. A lot of information will be covered. So to review this information at a later time, you can go to garrettmotion.com, racing and performance, how to choose a turbo, down to turbo system optimization. The Garrett Motion website contains a lot of helpful information. It contains product information about turbos, intercoolers, and ancillary components. It goes over Garrett's technology and product development, as well as our involvement in OEMs and motorsports. It contains tech tutorials written by the engineers from basic to advanced, up to expert level, where detailed formulas are used to plot operating points on a compressor map to help select the correct turbo. It also contains news and events, as well as a distributor locator. The website contains extensive information, both general and technical, and I encourage everyone to look through it. No matter what your experience level, I'm sure you'll find information that will help you in your specific application, or simply increase your knowledge of turbos and turbo systems. The most important thing to understand before designing a system is the application. Is it going to be used for road racing, drag racing, or drifting? Maybe it will be primarily a street-driven car. The intended use greatly affects the turbo selection as well as the system components. The turbo system that works well for a 9-second drag car is most likely not going to work well for a drift car or road race car. You need to have a target horsepower in mind. The horsepower value will be used to help design the entire system. For turbo matching, you can go to garrettmotion.com. Within the product pages, which are located at Racing and Performance, Performance Products, and Turbochargers, each page has a horsepower and displacement for that specific model. The keys to identifying your potential turbo match lie within these ranges. So it's important to have your target horsepower and engine displacement as you look for these turbochargers to align with your requirements. You could also use the Boost Advisor to assist with turbo selection. Additionally, you can review TurboTech's Basic, Advanced, and Expert, which are located at Racing and Performance, How to Choose a Turbo, TurboTech Expertise. Using the formulas in TurboTech Expert, calculate the mass flow and pressure ratio at redline for your specific application. Then you can plot this mass flow and pressure ratio on several compressor maps to determine the best fit. For the example in this presentation, the application will be a 400 horsepower street car using pump gas, therefore the estimated mass flow will be 40 pounds per minute. It is important that the air filter is sized for the maximum flow rate of the application. The target face velocity is equal to or less than 130 feet per minute at redline to minimize restriction. As excessive restriction can cause oil leakage at the compressor side piston ring, which results in oil loss, a fouled charge air cooler, and potentially smoke out of the tailpipe. Excessive restriction can cause an increased pressure ratio, which can lead to turbo overspeed. This overspeed then can reduce turbo durability and can result in an early failure. How do we determine the correct air filter size? For this example, the face velocity equals 130 feet per minute. The mass flow for our 400 horsepower application 40 pounds per minute, and air density at sea level. The formula that we're going to use, mass flow equals volumetric flow rate times air density. We want to solve for the volumetric flow rate, so this equals the mass flow divided by air density. Using the values for our example, the flow rate, the volumetric flow rate would equal 526 cubic feet per minute. If you have a twin turbo application, you would divide that flow rate by 2. Now we need to solve for the area. Using the formula face velocity equals volumetric flow rate divided by area, we solve for area, which equals volumetric flow rate divided by face velocity. Using our 526 cubic feet per minute volumetric flow rate divided by our face velocity target of 130 feet per minute, this equals an area of 4.1 feet squared. To convert this into inches squared, multiply by 144, that equals an area of 582 squared inches. Now that we have the required calculated area for the filter, we need to determine the correct filter to use for the application. In the chart to the right are some specifics on number of pleats, pleat height, pleat depth for some common filters. So for our example, we're going to use the pleat height of 9 inches, pleat depth of 0.55 inches, and number of pleats of 60. To calculate the area of this filter, you take the pleat height multiplied by the pleat depth times the number of pleats, and then multiply that by 2, since there are 2 sides to the pleats. Multiplying these together, the area equals 594 inches squared. Considering that 594 inches squared is greater than our 582 inches squared for the required filter, this filter is appropriate for the horsepower and the application. The oil supply depends on the bearing system in the turbocharger. There are 2 types, journal bearing and ball bearing. Journal bearings function similar to rod or crank bearings in an engine, where oil pressure is required to keep the metal components separated. In general, an oil restrictor is not needed for a journal bearing turbo, except for oil pressure-induced leakage. The recommended oil feed line is a -4 AN or hose or tube with an ID of 1/4 inch. You should always use an oil filter that meets or exceeds the OEM specifications. The oil supply for a ball bearing turbo is slightly different than a journal bearing. An oil restrictor is recommended for optimal performance. The recommended oil pressure at maximum engine speed should be between 40 and 45 psi. This normally equates to a restrictor with an orifice of 40 thousandths of an inch. However, you should always verify oil pressure entering the turbo after the restrictor. In general, oil leakage should not occur on a properly functioning system if the restrictor is not used unless the system pressure is excessively high. For a ball bearing turbo, the recommended oil feed line is a -3 or -4 AN or hose or tube with a similar ID. And again, you should always use an oil filter that meets or exceeds the OEM specifications. For an oil drain, generally a -10 AN is sufficient, but try not to have an ID smaller than the drain hole in the housing. To ensure that the oil drains out of the center housing via gravity, the oil outlet flange, when installed on the vehicle on level ground, should be plus or minus 35 degrees. And as far as the axis of rotation, which is the tilt, you should make sure that this is parallel to the ground within plus or minus 15 degrees. And you should always try to avoid undulations in the line or extended lengths parallel to the ground, draining into the oil pan below oil level, deadheading into a component behind the oil pan, area behind the oil pan where oil could be slung from the crankshaft, and if all of these things cannot be accomplished, a scavenge pump should be used to ensure that the oil is evacuated out of the center housing. A water-cooled center housing is a key design feature for improved durability. It eliminates coking by utilizing the thermosiphon effect to reduce the peak heat soakback temperature at the turbine side piston ring after engine shutdown. What is thermosiphon? Thermosiphon is a method of passive heat exchange based on natural convection, which circulates the fluid without the necessity of a mechanical pump. What does this mean for the turbocharger? After engine shutdown, the turbine housing heats up the water in the center housing, which lowers its density. The cooler, higher density water lower in the engine block pushes this water out, and then its temperature increases and the cycle continues. This circulation of water slowly cools down the turbocharger, which eliminates coking and other damage. To maximize the thermosiphon effect, avoid undulations in the water line. To ensure optimal durability of your water-cooled turbocharger, always install water lines and take care they are installed properly. This graph represents the effect of center housing orientation to peak temperature after shutdown. The negative degrees on the left side of the graph represent the water outlet of the center housing lower than the water inlet. The positive degrees represent the water outlet higher than the inlet. You can see the impact on peak temperature when the outlet is lower than the inlet. In effect, there is an undulation in the water passage through the center housing. This is why it's critical to orient the center housing so the outlet is higher than the inlet, so water flow always goes uphill even through the center housing. 20 degrees is a good target because the peak temperature performance and it's lower than the maximum angle of the oil drain flange of 35 degrees. Not connecting or improperly setting up water lines can result in damage to the turbocharger. Damage to the bearing can occur as well as coking on the turbine side piston ring, which can lead to oil leakage. This damage greatly reduces the durability of the turbocharger and emphasizes the importance of proper water cooling. For charge tubing, the tube diameter should be sized with the capability to flow approximately 200 to 300 feet per second. It is common to use Mach 0.3, which is 325 feet per second, as a guideline because for speeds of that amount, the changes of density are very low, around 1%. Selecting a flow diameter less than the calculated value results in pressure drop due to the restricted flow area. If the diameter is instead increased above the calculated value, the cooling flow expands to fill the larger diameter, which slows transient response. Using the 526 cubic feet per minute for our 400 horsepower application, a 2.5-inch diameter tube results in a velocity of 257 feet per second. This is within our target range, so it will work for our application, and luckily it's a common size for aluminum tubing. For general design guidelines, bends in the tubing should be at least 1.5 times greater than the tubing diameter. The flow area should be free of restrictive elements, such as sharp transitions or large area or shape changes. These best practices optimize system performance, but at some point the available space in the vehicle usually dictates certain designs. For charge air cooler sizing, visit the Garrett Motion website to review core sizes and their respective power levels. For our 400 horsepower application, there are a few cores appropriate for that power level. In general, use the largest charge air cooler that will fit the available space. Usually you run out of space before you use a charge air cooler that is too large. Proper manifold shape is critical in both minimizing charge air pressure drop and providing uniform flow distribution. Good manifold shapes minimize losses and provide even flow distribution. The side entry is ideal for both pressure drop and flow distribution, but is usually not possible due to the vehicle limitations. The manifold design affects the overall charge air cooler performance, so the design should be optimized within the space constraints of the vehicle. Charge air coolers are usually soft mounted using rubber isolation grommets. This type of mounting is also used for the entire cooling module. The design guards against vibration failure by providing damping of vibration loads. It also reduces thermal loads by allowing for thermal expansion. There are two types of blow-off valves, vent to atmosphere and recirculation, also known as a bypass valve. The vent to atmosphere blow-off valve is used on engines with a MAP sensor. For proper function, connect the signal line to an intake manifold source. Surge can occur if the spring is too stiff. The spring is usually replaceable, so if surge is occurring, a softer spring should be installed. The bypass valve is used on an engine with a MAF sensor. Again, the signal line should be connected to an intake manifold source. For optimal performance, position the valve close to the compressor outlet, but only if the valve is designed for high temperature operation. For bypass valves, surge can occur if the valve or the outlet plumbing are too restrictive. Using the proper blow-off valve affects turbo performance and durability. Therefore, the correct blow-off valve should be selected for your specific application and installed properly. There are two types of wastegates, internal and external. Internal wastegates are part of the turbocharger and integrated into the turbine housing. Most OEM-style actuators are not designed for vacuum. Vacuum can damage the diaphragm, which could lead to excessive boost pressure and engine damage. There are two options to connect the signal line to ensure only positive pressure goes to the actuator. Connect the line from the compressor outlet to the actuator, or the compressor outlet to a boost controller and then to the actuator. Using a boost controller will enable finer boost control than using just the actuator. Keep in mind, intake manifold pressure is limited by the spring rate of the actuator. So if using a boost controller and you still cannot increase the peak boost pressure, most likely an actuator with a stiffer spring will be required. The external wastegate is separate from the turbo and integrated into the exhaust. How the wastegate is integrated into the manifold greatly affects the flow capacity. While 90 degrees to the manifold is usually the easiest way to install the wastegate, this method can reduce the flow by up to 50%. The ideal connection is 45 degrees with a smooth transition, which is illustrated in the photo to the right. And just like the actuator for an internal wastegate, the signal line should be connected to positive pressure the same way, to the compressor outlet with or without a boost controller. The advantage of an external wastegate as compared to an internal is higher flow capacity and the ability to easily change the spring rates. There are a large variety of spring rates available for external wastegates, making them very versatile to meet your application needs. Oil leakage can occur from the compressor seal, turbine seal, or both. Leakage from the compressor seal is due to excessive pressure across the compressor housing inlet, which is caused by the air filter is too small or clogged, or charge tubing is too small or has too many bends between the air filter and compressor housing. It can also be caused by the turbo tilted forward past the recommended 15 degrees. Leakage from the turbine seal is caused by a collapsed turbine side piston ring, usually due to excessive exhaust gas temperature, or the turbo is tilted backward past the recommended 15 degrees. Leakage from both sides of the turbo can be caused by excessively high oil pressure, inadequate drain, improper venting of the crankcase, excessive crankcase pressure, or the oil drain flange is rotated past the recommended 35 degrees. If installed properly and the engine is in good operating condition, a turbo should not leak oil. System monitoring is critical for development and is used by OEMs, race teams, aftermarket kit makers, and even individual consumers working on their own personal cars. It enables the performance to be optimized, but also ensures appropriate durability. Two pressures commonly monitored are intake manifold pressure and turbine inlet pressure, which is commonly known as back pressure. Monitoring intake manifold pressure is critical to calibrating the actuator setting to achieve the desired boost pressure in order to meet the target horsepower. It can also help detect an overboost condition or damaged actuator diaphragm, which can also lead to overboost. Monitoring back pressure allows you to see the effect of the different turbine housing A over Rs. As the back pressure increases, your volumetric efficiency decreases, thus decreasing the ultimate power. It is helpful when fine-tuning boost pressure versus ultimate power. Two other commonly monitored parameters are exhaust gas temperature, EGT, and turbo speed. Monitoring EGT allows the engine calibration to be adjusted based on the temperature rating of the turbine housing material or other exhaust components, which affect component durability. Monitoring the turbo speed enables you to calculate operating points to plot on a compressor map and determine if the current turbo is correct for the application and the target horsepower. More importantly, it helps avoid a turbo overspeed condition, which can damage the turbo. The 11-point checklist is a quick reference guide when designing and optimizing your turbo system. The application information is critical and must be defined first. The target horsepower and intended use of the vehicle are used throughout the entire system design process. The air filter should be sized for your application needs. For oil supply, keep in mind a restrictor is recommended for a ball bearing turbo to optimize performance. The oil drain should have the proper size and routing. Water lines should be set up to optimize thermosiphon. Charge tubing diameter should be selected for your target horsepower. For charger cooler, determine the appropriate core size, design the manifolds for optimum flow, and soft mount the charger cooler for durability. Vent to atmosphere blow-off valves are for engines using MAP sensors, and bypass valves for MAF sensors. For wastegate operation, always connect the signal line to the compressor outlet, and for external wastegates, a smooth transition from the manifold to the wastegate is critical to optimize flow. System monitoring is used to optimize performance and durability. And finally, one that seems to be overlooked is system testing. Once complete, the system should be pressurized to check for leakage and periodically check clamp tightness and the condition of the couplers. This concludes the video presentation. I hope you found this information helpful. As I mentioned at the beginning of the presentation, this information is available on the Garrett Motion website, along with other general and technical information. Thank you for your time, and good luck with your future turbo projects.